Hello and welcome back. In this video, we will solve some problems using FFT. FFT is fast Fourier transform. It helps us to quickly multiply two polynomials of order n in n log n time. We are simply going to use this fact about FFT and not dive into the internal workings and the mathematics behind it. So let's directly jump onto the problems. The first problem states that you are given two arrays A and B, and we need to find all unique values of the sum of element of A and the element of B. The constraints are fairly large for all the variables up to 10 raised to 5. If we look at the brute force solution for this problem, we will simply use two for loops and store all the sums in a unique set and print that set. But the time complexity for this would be order n square, which is not feasible. Now let's try to understand how to wrap this problem around an equation of polynomial. If you simply create a new polynomial where the coefficients are 1 and the exponents are the values of arrays given, which are A and B, then the transformation to the polynomials will look as follows. Notice that the elements in A and B are not unique, so the coefficients can be greater than 1 after combining all the common exponents. Now, if we multiply the polynomial generated for A and B, notice that we get all possible sums in the exponents, because every possible term in the first polynomial will be multiplied with all the terms in the second one. So, for example, x raised to a1 will be multiplied with x raised to b1 and x raised to b2 and so on for all the values in array B. So that way, the exponents will get added and the x in the polynomial remains constant when we are multiplying two terms. So this gives us all possible sums in the exponents of the polynomial in the result. If we notice a fact about the resulting polynomial, we can see that the exponent, for example, c1 x raised to 1, means that the sum of elements from A and B is equals to 1, and c1 is the count of those number of pairs. Similar for c2 and c3. c2 will be the count of values where ai plus bj is 2. So the power represents the sum and the coefficient represents how many of them are there in the count. So this can be implemented as follows. On the left hand side, you can see the generic code implementation for FFT. We are going to treat it like a black box and not really care about its implementation and simply use the multiply function as provided in the interface. We initialize two variables for array A and B and also the polynomials for A and B. Then we use the subscript or the index of the vector as the exponent and the value that will be present at that index as the coefficient. Since the values in A cannot necessarily be unique, hence we are incrementing by 1 for each power, which means that let's say array A contains value 2 5 times, then the polynomial vector will have 5 at the index 2. Now we will simply use the product multiply function provided by the FFT namespace, and the product will be computed in n log n time. After that, if the coefficient is positive, that means that particular sum is possible and the exponent will be printed because that is the sum that we are finding out. That's it about this problem. The next level for this problem is to do the same thing, but instead of 2 arrays, you are given 5 arrays and we need to find all unique values of the sum of elements in each of them. The hint to solve this problem is same as before. In the same way that we created 2 arrays, 2 polynomials for the 2 given arrays, in this case as well, we will create 5 polynomials, multiply them and get the result as we saw in the previous problem. The next problem is from Code Forces named Thief in a Shop. We are given n items, each with a price ai, and we also have a knapsack which must exactly contain k items. and repetition is also allowed. We need to find all possible total costs of the values that will be present in the knapsack. Constraints are as follows. As we saw in the previous problem, we had to sum up two values from two different arrays. But in this problem, we are summing up k values from the same array with repetition. Hence, the equation for finding the total sum of elements in a knapsack will be as follows. Notice that I1, I2, I3 are indices of the array A and they can be repetitive, hence they can take any value from 1 to n. If we represent this sum in terms of polynomial, if we want to arrive at the sum in the exponents of the polynomial, we must multiply the polynomials k time one after the other, simulating the fact that we are choosing k items with repetition. And on the right hand side, you can see the exponent of x, which will contain k terms in the summation, meaning that we have chosen k items from the array A. If we simplify this product, we will simply arrive at the polynomial as shown in the yellow color, where we are simply multiplying the polynomial k times, hence the common term k comes in the power. The implementation for this is as follows. So in this case, we want to find out the exponent or the power of polynomial to the power k. We can use the similar concept as binary exponentiation. For example, if we wanted to find out a raised to 7, we find out first of all a raised to 1, which is the smallest power of 2, or the smallest bit present in the binary representation of 7, and so on. That way, we will dissect 7 into only logarithmic number of components and multiply them all together. This is called binary exponentiation, and you can also read about it more on the internet. On the left hand side, we will take in the implementation, we will first of all take the array as input. We are creating the polynomial in the variable p. We are inserting all the coefficients as 1 because we only care about whether that sum is possible or not. We don't need to count how many times that sum is computed. So the final vector contains the exponent to the k of the polynomial p. Next, we will perform the same operation as binary exponentiation, and inside the while loop, you can see there are two for loops which are essentially minimizing the values or the coefficients of polynomials with 1, because since k is fairly large, the coefficients can grow exponentially, and we only care about positive coefficients. Hence, even if the coefficient goes about 10 raised to 9, we only care about whether it is 0 or 1. So we are trying to keep the coefficients Boolean. That's the main purpose of those two for loops. And at the last, we will simply check if the coefficient is positive. That means that sum is possible. That means a knapsack with that sum of elements of exactly k items is possible, and we will print that value. The next problem is from Codeforces named Rusty String. You are given string as consisting only of v, k and question mark type of characters, and a question mark can be replaced with v or k. We need to find all possible values of period of s. Period is defined as, so let's say we want to check whether the given string is of period 2 or not. We subsequently take two characters and place them one after the other from top to bottom fashion. So for period 2, we take the first two characters question mark and v, then take the next two characters which are k and question mark, place them below each other and check whether all of them can be made equal in columnar fashion. Obviously, for period equals to 2, question mark can be replaced with k and the next question mark can be replaced with v, and that way both of these strings will become equal. For period equals to 3, we take the first 3 characters. After that, the characters are less than 3, so we take whatever it is remaining and place it below the first 3 characters. Now if you look at the column 1, you notice that there are 2 question marks and they can both be replaced with the same characters, either v or k, and that will denote that period 3 is possible. Period 4 is possible because there is no leftover string to compare it with, and it is only the singular one. If we have to observe for any particular period k, this is the generalized pattern for it. If we want to find out whether period k is possible or not for a given string s, we have indexed the string with 1 based indexing. Notice that s1 must be equal to s of k plus 1, and both of them must be equal to s of 2k plus 1, and they must also be equal to s of 3k plus 1, which is denoted by the red pattern in the diagram. Similar for s2, it must be equals to s of k plus 2, s of 2k plus 2, and s of 3k plus 2, and so on, which is denoted by yellow mark, and so on for the purple mark. This property must hold for the first k characters. That means if the period is k, then all the elements to the right which are at a distance of k must be equal. That is the main property. Now, how do we find out for all k possible whether this k period is possible or not? Instead, we can find out all positions where a period is not possible. How can we do that? We know that v and k cannot match, or k and v cannot match. Question mark can be converted into any of the characters. So we only care about what are the positions of v and k. So to find out all possible mismatches, notice that for period equals to 4, the first character must be equals to the fifth character. And in this example, it is not possible because they are different. And this also means that periods 1, 2 and 4 are also not possible, which are divisors of 4. This is true because for period 2 to be possible, it must have the conditions that s1 equals to s3 equals to s5, but s1 and s5 are already not equals. That means any divisor will also not be the period of the string. So the final solution that we will arrive at will be first to find all the periods that are not possible. To do that, we find all distances between all the v's and the k's. Distance between any character I, which is v, and any character j, which is k, is the absolute difference between their indices. Now, if you look at an example, here we have v present at indices 0 and 3 and k present at 4 and 6. Now, since we want to find out all possible distances between mismatching characters, we need to find the distances in the exponents of the polynomial. Hence, for v, we consider positive indices, and for k, we consider negative indices. But according to FFT, or the simple form of polynomial multiplication that we are considering, the exponents must be positive. Hence, we are adding a positive large values so that the total sum will always be the absolute difference, which is the distance that we require. But it will have n added. So notice that once we have multiplied these two polynomials corresponding for v and k, we will arrive at a polynomial where the exponents will be the distance between v characters and k characters indices, and the coefficient will be either 0 or 1, or it will be positive wherever that particular exponent or the distance is possible. So if ci, the coefficient of the resulting polynomial, is positive, then the period di minus n is not possible. Notice that we are subtracting n again, that which we have added in the polynomial of k. The implementation for this is as follows. First of all, we take n and s as inputs. Then we initialize two polynomials v and k. Then we initialize coefficients 1 for all the exponents in v wherever the position in s is v, and same for k. Notice that we have added n as so as to make the exponent in k positive, as we saw in the slide. Next, we multiply these two polynomials, and after this is computed, we will need to compute all possible distances where a mismatch is present. To do that, we will go over all the coefficients and exponents in the product polynomial and find out the actual distance by subtracting n, which we added in earlier, and mark these possible distances as true. On the right hand side, we can see that we are iterating over period p and checking whether it is possible. As we saw in this slide, if p is possible, then any of the divisors are not possible. If k as a distance is possible, then any divisors of k are not possible. So if we are trying to find out whether a period p is possible, then all of its multiple must not have any mismatch. So we are checking it by going over all the multiples of p and checking whether that possible distance is actually falls at all of the multiples places. If that is the case, that period is possible, and we simply print out the answer after that. Yep, that's it about this video. If you found this helpful, do let me know in the comments. See you again. Thank you.